Hey guys, welcome to 2.3 notes. The title of 2.3 is continuity. So the general idea behind the continuity, can I even write continuity, is any function such as y equals f of x that can be graphed without lifting up your pencil. Okay, so that means if you can't lift up your pencil, that means it has no holes, okay, or it just shouldn't have any asymptotes, no hole, no asymptotes, and no jumps. So discontinuity is the opposite of that. That means it has some holes, some asymptotes, or some sort of a gap called jump. Technical definitions for continuity at a point. You have two of them. You have interior continuity. So interior point, the definition is f of x is continuous at x equals to c if and only if the definition sets the limit as x approaches c of f of x is identical to f of x. So what that means is, let me just do a little sketch here. Okay, so let's do a little sketch of a makeup function. Here is, okay, so here's A, here is B, this is f of A, so make a dot, f of B somewhere up here, so do that one, f of B. All right, so here's f of A, f of B. So there, okay, do that. Now, C is an interior point, meaning that it's somewhere, pick a C value in between A and B. Pick a different color really quick. So let's say we want to pick this location. So here's C. Now, if you can see that this is an f of C, okay, f of C, the limit says the height, okay, as x approaches c, should be identical, change that to f of c. Sorry about that. The limit as x approaches c of your function, which is in red, it should be equal to the algebra value, okay? So that's when you know the interior point is continuous. You also have exterior points called the A and the B. Those are the endpoints, okay? So endpoint, you have two of them. So the first one is f is continuous at the left end point. In this case, based on our picture, the left side is A. So x equals to A if and only if the limit as x approaches a from the right of your function, which is made up as the red curve, has to equal to its algebra value, which is f of a. Case number 2, f is continuous at the right side, the right endpoint. In this case, we use b at x equals to b if and only if the limit as x approaches b from the left side of the function equals to its algebra value. So what this means is that the endpoint must be close for you to say that the endpoints are continuous, okay? Continuous on an interval is our next definition. Go ahead and find this. So a function is continuous on an interval let's call it from close A to B, if and only if it is continuous at every point on that interval. Okay. There are a few types of discontinuity. The first type that we have already seen in Algebra 2 was the whole. This is the removable, and there's a reason why it's called a removable. Okay. So back in the days, let's make up an IE first, and then we'll spell out the definition. IE down here. Back in the days, you were given rational functions. The simplest one I can think of is this one. Then we cancel out the x minus 1. So now your reduced function is 1 over x plus 2. Notice how you still have one vertical asymptote at x equals to negative 2. But what happened to the term that we cancel? Okay, so this was canceled. So technically, because we reduced that, it's still a restriction for x, right? But because we reduced that, it created a whole at x equals to 1. So a whole is a removable because we reduced it. That's why it's called a removable. So the definition of a removable is technically a whole. When the limit as x approaches c of your f of x function, it exists, okay, but not equal to f of c, okay? Because think about our IE down here. X can never ever be 1 and x can never ever be negative 2. But there's only one VA at x equals to negative 2. That means at x equals to 1, it still doesn't exist. So what that means is that there's no value at that location, but you still have a limit. So that's why definition of discontinuity, it makes a removable, aka a whole. Number 2, it's infinite discontinuity. So infinite discontinuity is not removable, okay? So this is not removable. So the definition is when the limit as x approaches c of your function does not exist because the limit as x approaches c from the right of your function equals to either positive or negative infinity, or the limit of f of x as x approaches c from the left can also be positive or negative infinity. So this is kind of talking about, let's talk about this component right here, right? So as you can see, the limit doesn't exist because at negative 2, you have a vertical asymptote. On the right side of negative 2, that means I'm coming from here. When I plug in, let's say, when I plug in, let's say, negative 1.9, right? Negative 1.9 plus 2, that's going to be a positive small number on the bottom. 1 divided by a tiny, 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 tiny positive number, it will give me a positive infinity. So that is going that. So by definition, this right here is going up. Now the other one, when I'm approaching negative 2 from the left side, that means I'm going to pick negative 2.001 plus 2. That's a small negative number. So 1 divided by a small negative number, that is creeping down towards negative infinity. So based on that, at x equals to negative 2, it's an infinite discontinuity. Normally, you can think of it as a vertical asymptote. 3 is a jump. Jump is another type of discontinuity. Again, this is also a non-removable. So the definition is when the limit as x approaches c from the right of your function is not the same as x approaches c from the left of f of x. Okay. We have seen this already. So one of the functions I can think of that keep reappearing in your homework assignments are this. Okay, so this is the piece I'm thinking about. So when I graph this out, or when I sketch this out, right, on the right side, it's always 1. On the left side, it's always -1. So if you can see, as x approaches 0 from the right and the left, they exist independently, they're just not equal. Okay. Okay, last one. Last one is a type of discontinuity, except that we will not be seeing it a lot in this introduction to calculus course. So oscillation or oscillating discontinuity. Again, this is not removable. The only removable is the whole at the beginning. So oscillating discontinuity is when the limit as x approaches c of f of x, it does not exist because we cannot determine due to too many, whoops, that's a funky M, too many oscillation. Okay, so many changes. And I believe I kind of introduced this a little bit before with oscillations. When you have a curve that changes so much that you can't really determine where the height is as x is approaching a particular number. So that's what it means by oscillation. Okay. Again, I said for this course of Calculus A, we don't really need to focus on oscillation as much. All right, and I think that's the end of the definition.